to be seen on YouTube, which you're free to, you can stay away from the cameras. So you can just, you will not be seen this way. So without much further ado, I would like to call Dr. Wong, the Associate Dean of the Graduate School, to say a few words.
Good morning and welcome on a Saturday morning. This is exciting, right? I think this is about my third TARDIS.
Second.
The second TARDIS. Last one was in the Gateway, and it is growing. It is exciting. I was there. I learned a few things. I'm a professor of geography, by the way. Oh, thank you. Okay. Good morning. Okay. But I am excited at what we're going to learn here in this TARDIS workshop. Because, of course, you know that we aspire to be a Tier 1 research university and all that goes with it, but that depends on grad students and your research productivity. That means you need to crack out the papers. It means you need to get a grant so that we can accomplish what we want to accomplish. And so I see this TARDIS here as one important step in our goal. And that is why the graduate school is fully supporting this activity. I'm excited that many more students wanted to get in that could get in, and that's why we have the live stream. So I think we have about almost 20 students who signed up to join this workshop by remote. And so thank you very much for coming here on a Saturday morning. One other quick pitch. This semester we're going to have a 3-minute thesis. What is that? You tell us about your doctoral research in 3 minutes. And you could win $1,000 cash. Of course, it means you need to distill your research to some very core, essential, and you can show us what it's all about. And so this one step towards that. One other final thing, this workshop here counts towards you're getting a travel grant. Remember, you have to attend 3 workshops to get a travel grant. This counts towards that. Okay? So again, welcome, especially to our speakers. I want to thank you very much for coming and for helping us to learn everything we need to do about statistics so that we can be productive. Again, thank you very much for organizing this. This is exciting. Thank you.
And now our distinguished mixed methods scholar, Dr.Abbas Tashakkori, will talk about statistical significance testing.
You talk about anything on all day. Good morning. It's good to have all of you here. I know you have to escape many things in your lives to be here, but it's a good day. There are so many of you. Hopefully all of us will learn quite a lot about the topic, and I'll tell you what the topic is. I was asked to spend about 7.5 minutes to talk about why do we need alternative to statistical significance testing. And 7.5 minutes to a professor, right? Let them stop me. Quickly, I'd like to set the stage for the day by talking about why is it necessary for us to have this meeting today. And some of what I'm telling you might be surprising. I'm an alarmist as usual, but we can talk about the trends in research methodology, and especially in the statistical testing, quantitative methodology that's coming up. As you know, in about the past 100 years, we have had these ups and downs quite a lot, but past 100 years, we have had movements and counter-movements in research methodology. In social sciences in general, has spilled into methodology. Early last century, we got entrenched heavily in positivism. With the strict emphasis on causality, causation, finding the causes. Give me the cause, I give you the effect. Give me the response, I give you the stimulus. Give me 100 kids and tell me how many musicians you want, I give them to you. I mean, that kind of stuff, that kind of strict positivistic point of view. And at the same time, during the same period of time, 20s, 30s, Fisher, Neiman, Pearson, a number of people tried to come up with experimental designs and ways to test hypotheses, and the idea of significance testing came out of early last century, about 20s and 30s. Fisher produced significance testing, and Neiman came up with the idea of hypothesis testing, and both of them were based on some kind of a experimental framework, null hypothesis testing, and so on and so forth. In about middle of the century, something happened. When we switched as a counter movement, we tried to come up with post-positivism, in which we smooth up a little bit of causality argument. We we brought in the cultural factor, we brought in experimenter affecting experiments, and we came with probabilistic causality and relationships and all of that good stuff. And we had Campbell and Stanley and Cook, later on, much later, Shadish and so on, write about regression discontinuity designs and quasi-experimental design. So we tried to smooth out a little bit of that sharp edge in the middle of the century. In psychology, we went from Watson to the new behaviorists and all of the story about cognitive behaviorists and so on. And we switched that way, but we never got rid of the initial significance testing framework. We combined Fisher and Neumann and Neiman, and we still kept majority of our publications with that kind of a framework in which we hypothesized that there is a world, H0. Under H0, we made an assumption, and then we looked back at the data and said, does the data fit that assumption or not? What does the data says about, what does the data say about null hypothesis? And that link, testing the hypothesis and making a conclusion based on that kind of argument, went on and on. We never got rid of that. We went to the point that practically we couldn't publish without a P in our paper. P-value, I mean, if you didn't have a P-value in your paper, and the smaller those zeros were, P smaller than 0.05 wasn't good enough, P smaller than 0.001 was much better. We talked about more significant. I mean, we talked about significance as if it was a measure of validity, how credible the result is. It's significant, it must be valid. P smaller 0.05 level, P smaller than 0.05 became our measure of cutoff point for objectivity. If it's less than 0.05, it's good, it's objective, we reject the null hypothesis. So we built that system and it continued until very late recently. There were voices of dissent during this time, starting from 1930s, but especially the last part of the century, 1990s, around 1990s, Bruce Thompson and, oh God, I can name name after name, people who started saying, we don't want significance testing. We want something else. We went to effect sizes. So we made effect sizes mandatory by going through APA and AURA, and so effect sizes became mandatory. Then we said we want confidence intervals. So we made confidence intervals optional. It's not mandatory, it's optional. So we tried strong voices against that P smaller than 0.05 or 0.05, whatever it had to be, came up, and little by little there were suggestions to replace them, not replace them, accommodate to them, or add to them. Confidence intervals and significant and effect sizes were there. And to some extent we dealt with the problem, at least temporarily. We put a band-aid on it in a way. There were two major focus areas from the people who were dissenting, quote unquote, who were objecting to all of this. There were two major focus areas. One was based on the process of usage, that we are using significance levels correctly, we are making conclusions about importance, because it's significance, we call it importance, magnitude of effect came up, and so on and so forth. And we dealt with them to some extent, and we kind of diffused it, but they never went away. Because still you see the journals, you go there, and you still see the same patterns. Some journals, journal mixed method, I was the founding editor. We tried to stop P smaller than 0.001 kind of a thing, and it didn't really get far in, to some extent. Still we tried. Some journals have started going further than that, and in a minute I'm going to talk about it. The second more serious dissent is coming based on a philosophical, logical kind of argument. That it doesn't make sense for us to assume there is a H0, there is a world there, and look at the data, and look at H0, and if the data doesn't fit the H0, we say, okay, we reject the H0. It doesn't say anything about H0 anyways. And then what? We don't know what to do with the research alternative hypothesis. We reject the null hypothesis, but we don't test the alternate hypothesis. We don't have anything about any confidence there. We don't have any assurance that it will occur again. There's no prediction about occurrence in the future. We never directly test our hypothesis, null or otherwise. We test the null hypothesis, If the data contradicts it, we quote unquote reject it, we don't, then by default, we go back to the next one, which is one alternative hypothesis. Is it different? No. Yes. Are the groups different from each other? Null hypothesis says they are not different. Then we go forward and say, oh, the groups are different, and we never test the difference hypothesis directly. So that was one problem. The second problem was the issue of, we have alternative hypotheses, and when you reject the null hypothesis, you have a cutoff point, is a yes, no. What if your results say p smaller than 0.051? Right? It's not 0.05, so what do you do with it? Then that kind of binary, and I know I might be going into it, well, I don't want to spoil the surprise. So that binary problem was always there, and we never know anything about it. We never get a chance to test multiple hypotheses with a certain degree of accuracy or confidence. Like H1, H2, H3, we have this confidence in H1, we have confidence in H2, we have this confidence in H3. We never did that. We tested, going back to Fisher. Fisher used a modified Bayesian model, which I don't know much about, in which he assumed the probability of the results given the null hypothesis. And then we made all conclusions based on that. If we need to reject the null hypothesis, which is problematic right now, then we need to find out what is the probability of a null hypothesis given the data, and then go on. And even that is flawed, and I'm sure we're going to listen to some of that today. We go on. So to go back, there is a strong wave coming up against null hypothesis testing, and is widespread. And I think, in my view, we are at the tipping point. We have gone that for about 20 years. It started from 1930s, though. It's not that. The last 20 years, people have been talking about throw the baby out with the bathwater. Journals have started reacting to it. There are some journals now that they don't want the P in the papers. I mean, p-value. Sorry. Journal Basic and Applied Social Psychology outright does not publish anything that has a T, P, F, chi-square, any of those signs in it. They are not publishing. I mean, it's on the editorial board, and I know that for sure. And that's the first one, maybe strictly banning hypothesis testing. Other journals are coming up. Educational Psychology, the flagship of we are the Department of Educational Psychology, right? The flagship is moving. 2015, the new editor is moving in that direction. Is moving from this publishing purely automatic, robotic hypothesis testing like we did before. And other journals are coming up. Time will tell, I might be totally wrong, but sooner or later we have to deal with it. So, ask again, why do we need alternative to hypothesis testing? That's why you're here. We have two very esteemed scholars here that we respect very much, and they will give us two of those alternatives. Why do we need alternatives to hypothesis testing? One is about me. I've taught statistics for many years. Some of you are teaching statistics for many years. We teach introductory statistics, 5210, 6010, blah, blah. If I don't teach Z, T, sampling distribution, type 1 error, type 2, if all of those are irrelevant sooner or later, what the heck am I going to teach? Right? And some of you are doctoral students, you will graduate, you will deal with this sooner or later. It will come. The wave is coming. So we need to know what we're going to teach, right? The second one is about some of you. Publish or perish. I don't want you to perish. If you're going to publish so that you don't perish, you need to know the alternatives. Because again, as we go forward, all of these little bodies are going to go on. See, major journals are coming up and they're taking a stand against it. I don't have that kind of a power, prediction. I can't predict what the future would say, but I can see it's coming. In order to be able to publish, you need to get away from P and F and Z and chi-square and R square. And I mean, we need to get away from that to some extent. There are alternatives that are being suggested. There are a number of them. Two good ones are being discussed today. And with that, I'll let you introduce our esteemed colleagues. I am all eager to hear. Thank you.
Thank you, Abbas. You should teach 6010.
Tell me about it. Why not?
to invite Dr. Jeff Gill, our esteemed speaker, one of our esteemed speakers. He is Professor of Political Science, Biostatistics and Surgery, at Washington University, St. Louis. He is a widely published scholar. My first introduction to Jeff, not physically, was through his book called Bayesian Statistics for Behavioral Scientists. I'm not saying the name of the text correctly, but it doesn't matter because it's an amazing text. If you Google it, you'll find it. He is the winner of the 2009 Gosnell Prize for the best work in political methodology presented at any political science conference. That's a lot. You know, there are a lot of political scientists, too much actually. So that's very impressive, and we are really looking forward to your talk, Jeff. Thank you.
Thank you. Hey, I did it right.
And in the middle, if you feel like people are getting very excited, then you can let us take a break for 15 minutes, maybe around 10:30.
Start waving.
Yeah.
Well, thank you so much for the introduction, and thank you for the invitation to be here. I'm thrilled to be here talking about this, and what a great introduction. Where is he? There he is. Because it's a perfect setup for what I think the two of us are going to say and address. So this is who I am. This is actually a screenshot from my HR page. I think I'm the only professor of political science and surgery in the world. I've yet to meet another one. The truth is I'm a statistician and I study humans, right? So, but that doesn't go on my human resources webpage, so you get that. I'd like to talk to you today in two phases. The first phase is just sort of general discussion about why you should think Bayesianly. And then the second part is going to be a hardcore, here's how you do it session with code in JAGs and integrals and derivatives and cool things like that. So that's the plan. I don't see anybody running for the door yet. So a couple preliminary things. I'm supposed to do this disclaimer thing. The med school makes me do that. I have colleagues who get money from drug companies. I'm really jealous. But so far they haven't contacted me. Don't write down any code. It's all on my webpage, either on syllabi or in the computing section or whatnot. And the thing is, when you write down code in a lecture, you get it wrong anyways. You leave out a comma, and then you're banging your head on the keyboard for an hour. So don't do that. That's my webpage. And I want to tell you, I'm going to be fair and balanced about this Bayesian versus non-Bayesian thing. I'm going to be absolutely as fair as Fox News. So just keep that in mind. So what is all this Bayesian stuff anyway? So I get this question all the time at conferences. It's really fundamentally about overt and clear assumptions. Bayesians were so defensive for 100 years that we were so forthcoming with all of our assumptions. We just put everything on the table in a way that other folks don't. I'll be very specific about that. It's also a way to make probability statements about things. That is, to a Bayesian, everything we don't know for a fact gets described with a probability distribution. That's a terrific way to proceed. That's a great way to think about uncertainty. And again, I'll be very specific about that. And you know what? We take those probability statements and we update them as new knowledge comes in, as new data comes in, right? So we learn. So here's a process I want to describe to you. We know some stuff, we describe it. We learn some new stuff, and we update our theories and conclusions. You know what that's called? Science. Right? That's a very scientific way to proceed. It's also, we can absorb qualitative knowledge into our models through the prior distribution. I've done that through interviewing elites and things like that. So in some of the social science fields, as you well know, there's this qualitative-quantitative divide. Well, that's silly. If you can put qualitative information into your statistical model, you don't need to worry about that stuff. We also can change our parameter estimates over time in that learning sort of way. So I can't think of, actually, I'm going to show you one example today. I only know one example where things that are measured about humans don't change over time, right? You know, the probability of India and Pakistan going to war changed in the last 24 hours. Well, hopefully not much. You know, the probability that someone decides to vote or join a social group changes all the time. So why would we pretend that we have these fixed parameters? Well, the reason is that in the late 19th century, in the adolescence of statistics, most of what they were studying were fixed physical parameters, like the speed of light, and variance came from measurement instruments. Well, that's not how I work. I study humans. They change. They're volatile. They're weird. They're hard to measure. And then finally, it's going to be free from the null hypothesis significance test, which is a totally bankrupt procedure, as we heard already this morning. By the way, feel free to interject, ask a question, throw something at me, whatever. So I want to talk first about the typology of statistics. And this is something that people don't appreciate enough in the social sciences, I think. So it turns out that there are three types, so there's really two types of statisticians, but the first is frequentists. And I go to conferences in political science or sociology or whatever, and people say, well, I don't know about that Bayesian stuff, I'm a frequentist. And I go, BS, you're not a frequentist. You get one data set, right? You get the GSS data set. It's never going to change. It was collected in 2012, right? And you're a likelihoodist, right? A frequentist, a true frequentist, as we heard a bit this morning, a true frequentist has an unending stream of IID data coming at them all the time, okay? And if you go back and you read Neyman and Pearson's original papers, which is a fascinating exercise, by the way, they have theta A and theta B. And when you reject theta A, you accept theta A. Now, this is beaten into every one of you in some class. You never accept a hypothesis. They accepted hypotheses. And the reason they could do that is they had an unending stream of IID data. So their alpha over time became a probability. Right? That's shockingly different than the way almost all social scientists work. Right? I get a single data set. It's never going to change. It's sitting on my hard drive. Right? So people that do that kind of work are likelihoodists. Right? So that's the difference between the first and the third. Well, Bayesians are different. So we have this tradition that comes from Bayes, Laplace, DeFinetti, where we treat everything probabilistically, as I said. And of course, I'm going to go into that in detail. What is a likelihoodist, though? So it turns out that every likelihood-based model, everything that you do, is a Bayesian model with the appropriate uniform prior. It's a special case of a Bayesian model. So everyone in this room is a Bayesian. You just didn't know it until this morning. But it turns out humans are very Bayesian processors, right? We have just general knowledge about stuff, and we make decisions based on loss functions of knowledge, and we update those decisions. So if I'm going to jaywalk across the street in St. Louis, where the drivers don't really respect pedestrians very much, and it's one of those really clunky cars with the radio antenna is like a coat hanger, and you know there's different color paint on it. I'm going to look at that and I'm going to go, I don't think he's going to stop for me, right? So I'll wait. Now, on the other hand, if it's a brand new Mercedes, I go, well, he doesn't want to get sued. I'm going, right? So we make all of these Bayesian updating decisions based upon knowledge all the time. It turns out we're bad Bayesian processors, but we're Bayesian processors. So it always sort of bothers me when people call themselves frequentists when they're really not. So for the next few minutes, since likelihoodists are special cases of Bayesians, I'm going to spend about 5 minutes talking about differences between frequentists and Bayesians that are really important. I'm going to get the obvious and important one out of the way, okay? Which is visual differences. So this is just pictures from a recent political science conference. You know, depending on what kind of paper was being given. But one difference is what is fixed, okay? So to a Bayesian, what's fixed is the data. Hey, I got the data, it's there. I can go on vacation, leave my laptop at home, go somewhere nice, come back a month later, I never do that, and it's still there, it hasn't changed. So to me, when I get the data, it's a one-time off event. That's how human data is generally collected, and it doesn't change. What's unknown are the parameters that I care about. Okay? In contrast to a frequentist, the data are an IID random sample. That's the variable thing. The parameters are fixed by nature, and they're trying to obtain knowledge about those parameters. So that's a very backwards relationship. What about interpretation of probability? Well, to a frequentist, and this is where the name frequentist comes from, it's the probability that's observed from a long-run process. So if I want to know if a coin is fair, okay, I just lost my thing. I'll just yell at you. So to a frequentist, if they want to know if a coin is fair, right, what do? You hire a bunch of undergraduates and you flip that coin into a sand pit all day, right?
Would you like a mic?
No.
Or does it
I'll just yell. Actually, here he comes. What would you do? You just frequently do that experiment. That's an IID set of independent, or I don't need to say independent, IID set of data coming at you, right? So to them, probability is a long-run process from experimentation. So they care about the probability of the data given some hypothesis. Now the turnaround on that is so Bayesian. Yeah.
I think he's a frequentist.
Minor technical problems. That's it, I can go home now. All right, we did it. So to a Bayesian, right, it's the degree of belief. Probability is what you would bet with your own money, okay? And so Bayesians care about the distribution of some unknown parameter given the data. Yeah. Okay, so that's another difference. What about general inference? What do frequentists do? Well, they care about point estimates and standard errors and confidence intervals, right? They want deduction from the probability of the data given H naught by setting alpha in advance, okay? You accept one hypothesis and you reject the other. That accept word, just every time I say it, it feels funny. Bayesians, they're interested in induction, right, from P of theta given the data, starting with a prior, like what do I know before I got my data? Do you really want to read a paper by someone who didn't know anything before they got their data about the subject matter? Right? You know what a literature review is? It's a set of priors, right? And then we do broad descriptions of these posterior distributions, and we have our version of an interval and so on and so forth, which you'll see. What about quality checks? So frequentists tend to care about type 1 and type 2 errors. Sometimes they care about effect size and power, which was discussed earlier this morning. Usually there's a fixation with small p-values. How many stars can you put on the table? Right? Stars are stupid. Everyone say that with me. Stars are stupid. Right? And most people don't realize that 3 stars doesn't mean the null is less likely than 1 star. How'd you get those stars? Step 1, assume the null is true. Right? See, I lost my place now. I got so worked up. What do we do as Bayesians? We do posterior predictive checks. That is, we compare our predictive inferences with the data. We do sensitivity analysis with our assumptions. We're very sensitive about our assumptions because we had 100 years where people were attacking us for that. And we have some very formal mechanisms, which I'll show you today. The BIC and so on and so forth. So here's some reasons not to use Bayesian inference in the social sciences. And remember, I'm fair and balanced. Okay? First of all, the population parameters you have are truly fixed by nature and they never change. Okay? Secondly, you do not have any prior information before you started the study. None. Third, it's necessary to provide results as if you had experimental control. Fourth, you care more about significance than things like effect size. Your computers are slow and relatively unavailable. Okay? And finally, you want automated cookbook type procedures. So if that's you, you should go. A few of us are not going to help you. All right, so fair and balanced. I have to give you the other alternative. And by the way, my graphics are also fair and balanced. So why should you be Bayesian? Okay? You want to be very careful about your assumptions, and you want to be very clear about them. You view the world probabilistically, and you want to express that in how you write and how you do research. You realize that every statistical model ever created is subjective.
So it's really kind of bizarre, but one of the main criticisms of Bayesians in the mid-20th century was that we were subjective because we used a prior distribution. Well, it's also subjective which likelihood function you pick, where you get your data, what estimator you use, what software you use, how you write it up, what your table looks like. Everything is subjective, right? So, and finally, the prior information abounds in your literature. You know stuff, you've read stuff. How many people have read stuff? Right, so you have priors. Okay, so it's still, nobody's running for the door. So there's some problems, some of which were discussed this morning already. I'm going to repeat because they're so important, with standard social science statistical thinking. One is this idea of small n inference. So I work in some literatures where some people have gigantic data sets and some people have small data sets. And a subset of the people with gigantic data sets, they put stars all over the tables and they look down on people that can't do that. Well, that's ridiculous. It doesn't mean you're doing better work because you have bigger data sets, right? So that's the first 2 points, actually. And then there's confidence, and I'm going to talk about that in detail, so I will talk about that now. There's a bunch of buried assumptions I want to also talk about, and then I want to bash the null hypothesis test a little bit. By the way, that's another graphic from a recent statistics conference. I think that was me right there. So going back to that large versus small data thing, Bayesian work really, oh, I'm back to that. That's good. I feel like, one of those talk show hosts. Jerry Springer without the violence. Does that work? Hello? Hello? It's green. Okay. Yeah, I hear myself echoing. There we go. Okay. This is better, yeah. So one of the things Bayesian work helps you do is work with smaller data sets and still say something rigorous and scientific. So I want to just contrast how silly this data size thing can be. So on the left-hand side is a graphic from SETI. How many people know about SETI? Why is it always like the more senior people? You're right, maybe we're a product of our age. SETI stands for the Search for Extraterrestrial Intelligence. Did you ever have it on your computer? No? So here's the deal. You go to this webpage at Berkeley, big surprise, and you can download a piece of software, and what it does is when you're not doing your own work, it's downloading data sets from Berkeley, and these are data sets on radio signals from space, okay? And they're highly processed signals, and it's the idea that this is actually kind of a fuzzy graph. I keep meaning to replace it. That if you're like, the tiniest epsilon outside of these lines here, then it's an unusual signal that doesn't seem random in some way. And therefore, it might be extraterrestrials trying to talk to us. This is true. You can do this if you like. You swear you've never done it. And it sits on your computer, and it's not bothering you any. And here's the cool part, is that if in fact it is an alien talking to us, you get the credit for the discovery. Isn't that neat? Like, you'll be famous. And so this thing here is built upon billions of samples of radio signals. And the reason you can make that incredibly fine distinction, just epsilon outside of those bounds, is because you have billions and billions of data points. Okay? Now, on the other hand, here's some real work. This is marriage rates in Italy from 36 to 51, right? So it's 15 years. Wait a minute, it's 15 data points, right? How many people have done inference with 15 data points? Besides me. I'm doing it right now. One person, yeah. That's about, it was hard, wasn't it? So here what we're doing is, it would be very difficult to make some statement non-Bayesianly about this. What this is about is assuming a distribution and then aberrations from the distribution, right? So what it is there's a mean, which is the dotted line there, and then these are data points. These are marriage rates per 1,000, okay? And you see they're pretty high there. they dipped in the 1940s. So it turns out there was this little fracas in Europe in the 1940s. It was in all the papers. You may have heard about it, right? And then after the dip, there's a big jump, and then it settles back down. Right? So what happened? Well, the Italian soldiers went off to Africa and wherever, right? And they weren't marrying their sweethearts. They came back and they made up for it, right? But there was still an underlying propensity, tendency for marriage in Italy. It's just that it got temporarily suppressed. So the distribution didn't change. The distribution was the same. The desire was the same. But there was an event, right? And so if you have 15 data points and you have to have an indicator function for war, you've just chewed up another degree of freedom. I mean, how awful is that? But if you assume there's an underlying distribution, you can discover things, right? But you can't do things like that if you're non-Bayesian, or at least it's extremely difficult. Confidence. I love confidence because it is the most frequentist idea on the planet. Okay, so which one is correct? It's an interval that has a 1 minus alpha chance of containing the true parameter, or an interval that over 1 minus alpha % of replications contains the true value of the parameter on average. How many people think 1? Good. 2? Raise your hand. Really high. Only one person? 2 people? Right, it's the second one. How many people have taught confidence intervals to undergraduates? Was it fun? Was it fun? No, it's horrible. Right? Because they want it to be the first one. That's what they want it to be. That makes so much sense. By the way, that turns out that's a Bayesian credible interval, the first one. We'll talk about that in a minute. It's the most frequentist idea on the planet because you say, well, I've got one data set, I've got one study. Oh, but if I had 19 more, that's what this thing would be. That's incredibly frequent. So I have this unending stream of data coming at me. I can do all the experiments I want. The most frequent statisticians in the world are people that do industrial quality control. If I worked for Apple Computer and I pulled 3 circuit boards off the line every day and tested them every day, I'm a frequentist, right? I would love to be a true frequentist. I'd love to have IID data coming at me all the time. So I just replicate my experiment 19 more times. But we're often, typically, not in a position to do that. So I said I didn't think there are any human parameters that are truly fixed. I think I found one. It has to do with confidence intervals. So, 15, 20 years of teaching, what I found is that when undergraduates take the midterm and there's a confidence interval interpretation question, 50% of them get it wrong. Okay? I thought, am I doing something here? So 8 years ago, this semester, I did an experiment. I spent 2 weeks on nothing but the confidence interval. 4 lectures. 6 hours. Yeah, 6 hours. On just the confidence interval. I did the theory. I did examples. I did simulations in R. Right? I did all kinds of things. I finally, at the end, I said, just memorize these 2 sentences. Right? The exam comes a week later. Guess how many people got it right? 50%. So, either I'm an incredibly bad teacher, or that's a fixed parameter by nature. Actually, both could be true. So this is kind of a silly concept, as we already heard this morning, to tie ourselves to, right? This confidence interval thing that really we're not doing. Okay, how about varied assumptions? So I mentioned that Bayesians are very overt about their assumptions. Other people are not. So every Bayesian model, every non-Bayesian likelihood model is equivalent to a Bayesian model with uniform priors. But you don't have to defend your uniform priors. Isn't that weird? I have to defend my priors. Why don't you have to defend yours? We have tons of models where normality is swimming around in them, and we don't defend it. Like, if I go do an ANOVA, just a standard classic ANOVA, I basically don't have to talk about normality of various properties. I just do it. My favorite is the correlation coefficient, right? So the correlation coefficient is a regression slope. You know this, if you multiply by the standard deviation of x over the standard deviation of y, you get beta. Right? Now, if I give you a regression slope without a standard error, and you're a reviewer, what are you going to do? You're going to trash this thing, right? But how many people give a correlation coefficient with a standard error? Like almost nobody. Me. person? No, nobody's raising their hand. The other thing is a correlation coefficient is a linear model, right? It is basically regression, but you don't have to defend linearity. People just spit out correlation coefficients all the time, right? As evidence without defending any of those aspects. Now, how about only 2 models are tested? So here's how the classic social science article gets written. Here's an important literature. Oh, I have a new theory. I got this data set. Here's the model I ran. Look at these results. Let me tell you why they're important. Right? Isn't that the recipe? Write that down. Do that and you'll be successful for your whole life. Wait a minute. Here's the model I ran. I talked a little bit about this yesterday in political science. The model I ran, I know one person who ran one model and published it. One person, and he's really proud of that. Like the first model he ran. We don't do that. We run several models. We're investigative, we're curious. We want things to fit well. We're still theoretical, we don't data mine or model mine, right? So why do we have to say in our article we ran one model? The model I ran. It's just bizarre. So what we do is we have theory, we have variables, and we construct something that makes sense, and we try a few different things, but you're not allowed to say that, right? So a few years ago, more than a few years ago, I had this data set, and it had 20 variables, so I could build over a million, slightly over a million models. If you sort of come, it's 2 to the k. I ran a million models, for real. So the outcome was coups in Africa. There were a bunch of demographics on the various countries and other variables. And so I ran about 1.1 million models. And do you think I really typed those all in? No. I wrote a little wrapper in R that combinatorically ripped through all the models with 19 parameters, 18 parameters, 17 parameters. And I let it run over the weekend. Okay, and then I came in Monday. I wrote a little Perl script that sort of pulled out 100 or so of the obviously good models. And then I went through those by eye and I pulled out like 10, 12 or so that just like looked like they belonged in a journal. You could put stars all over them. Don't do that. And then, so I took those 10 or 12, and I took them down the hall. There was a guy, Jorn Heiden, who was considered one of the leading figures in African politics as a scholar. And I put him on his desk, and I said, which ones of these do you like? And he stared at them for like this really uncomfortable 20 minutes. He didn't know what I was up to. And he said, you know, Jeff, I'm really sorry. None of these have anything to say about how African politics works. Right, so what did I do? I data mined, I model mined, and I got nonsense because I was chasing significance, chasing stars, right? So we should be able to admit that we can do more than one model, right? And that we do specification searches. There was this guy, Ed Leamer, in the 1980s, who sort of bemoaned how the social sciences do this model hunting process poorly. And we should admit that we do a little bit of that because we're theoretical. And if I have ideology in my model, and there's 5 variables that measure ideology, which one do I want? You know the answer. It's the one that fits best, right? Did I get another one? This is great. I'm going to look like Iron Man.
You can take out the old
It doesn't have a clip. Yeah. So just stick it in my mouth. You want this one back, or is it like redundancy? Oh, thank you. All right. Now I'm even louder. I don't think you want that way up high. How's that? Okay. So, anyways, that's just a cool-looking crypt in Moscow. And we did hear some words about this morning. Thank you very much for that intro. It turns out the null hypothesis significance test is wrong. It's not flawed, where it's non-optimal. It's just flat out wrong. Okay? So, and many people have said this. This is like 1/100th of the literature. We sort of got introspective on this after a guy named Merton in 1962 wrote an editorial for one of the psychology journals and said, hey look, we're a better journal than we used to be. So we're not going to take results at the 0.05 level. We're only going to take results at the 0.01 level. What? So the psychometricians of the time revolted. Or they were revolting, I forget which one.
And that started this gigantic literature, but most people still don't pay attention to it, which is just bizarre. So there's several reasons why, and I'm going to go through some of these in detail. But that I already talked about. The arbitrariness of alpha. This is so silly. So do you guys know where 0.05 and 0.01 really come from? Manure. Manure. I can't say the other word for it because I'm being videotaped. But you know that word. It starts with an S. And here's where it comes from. At Fisher, in the 1930s, he was doing these experiments, which was alluded to this morning. He was trying to grow corn under different conditions, different sunlight, different levels of manure. Okay? He's writing about it. He said famously, these are just convenient levels. He used the word convenience in his book, Statistical Methods for Research Workers. I love that title. Because to me, it sounds like welding. You know, it's very blue collar. You know what I mean? And so, so he said they're really convenient. And they became convenient for the following kind of weird reason. Has anybody done this? Sometimes it's an undergraduate calculus exercise. Have you ever integrated the normal distribution? 2 people, 3 people, right? Did you enjoy it? No, you didn't, because you had to put it in polar coordinates, right? There's no antiderivative for the EXP part of the normal PDF. So it shows up in some like undergraduate calculus exercises, right? Just as a way to torture young people. Anyway, so Fisher, what he did is he built those tables, and those were publications at the time, which is really kind of interesting. Courtesy of JSTOR, you can go back and see that. And what he did is, he didn't actually do the integrals, he handed it to his computers. I'm reading this, I'm going, his what? His computers. And I had to figure out what that's about, right? We didn't have computers in the 1930s. It turns out their computers in England at the time were these women that were really good at rote calculations, like integrating the normal over and over again at different levels to build a table, stuff like that. And it's actually really cool historically, because when, you've all seen the movie, I'm sure, when during the war, the British built Bletchley Park to decode the Enigma machine, they had to do a lot of boring rote calculations. They said, who's really good at these things? And they didn't find similar women, they found the exact same women. They found Fishers and Neymans and whatnot, and Wald's women who were really good at these repeated calculations, and they brought them to Bletchley Park. That's really cool. So anyway, so Fisher hands this to his computers, he builds these tables, okay? Nobody likes integrating the normal PDF. So if you're a scholar at the time, you say, well, you know, I really like 0.025, that's kind of cool. 1 out of 40 is neat. And you know what, I don't want to do that, I'll just use Fisher's values, is what people did. And up until, I think about the 1970s or 80s, if you opened an intro stat book and went to the back, look at the tables, they still cited Fisher at the bottom of the table. Fisher didn't invent the normal cutoff points, right? Or, you know, the normal distribution. He just made the tables and published them. So, so that comes from manure. And there's another problem with this. And this is kind of surprising. Alpha 0.05 is a serial killer. It's a murder. I'm not joking, right? So 50% of my time I spend in the med school. And in medicine, 0.05 is holy. You think we're slavish to it in the social sciences? We don't hold a candle to biostats and medicine in this regard. It is holy. So if you submit your grant to the NIH and you don't do a sample size calculation that shows that you can get alpha 0.05 and power 0.8 or better, you will not get funded. Right? Never mind that you don't even have the data yet, right? So it's a fiction anyways. But it's a serial killer because decisions are made all the time, every day. Medical decisions are made every day based on 0.05. Let me give you a really stark example. So 2.5 years ago, there was a breast cancer drug in a stage 3 clinical trial. And if you don't know, those are usually big, right? And you try and pick up pieces of the population you didn't have earlier. They're pretty much confirmatory. So there was a breast cancer drug, thousands of women in the clinical trial, okay? Get to the end of the clinical trial, it didn't make alpha 0.05. And the FDA said to the drug company, you can't sell that drug. Off the market forever. based on 0.05. Okay, so this is a big deal. I don't know if you remember, but there were hearings in Congress, and women went to DC and testified, and they're crying at the table saying, this drug was saving my life, and now I'm going to die because I can't have it anymore. And the FDA guy stands up, and he says, hey, we need a threshold. That's the one we've been using forever. We need a criteria, a decision point. That's what we're going to do. End of story. Gavel hits, gone. So 0.05 is literally a serial killer. We lock up our other serial killers, don't we? So don't be slavish to that. And I'm going to talk about the other two in detail. So here's another problem with the null hypothesis significance test. It's based on this thing called probabilistic modus tollens. Okay, now modus tollens is fine. That's what you see here. I should take, oh, I did take it off. This is regular modus tollens. This is fine. If you go to the philosophy department, where is the philosophy department? That way. And you ask, is modus tollens okay? They'll say fine. That way? Okay. So if A happens, then B. But wait a minute, not B is observed, therefore not A. And they'll say that's fine. Here's a hypothesis tested version of that. If the null is true, the data will follow an expected pattern. Wait, the data don't follow an expected pattern, therefore the null is false. Now, the philosophers will say that's fine. That's not the problem. The problem is, we make it probabilistic. If A, then B is highly likely. Does that sound familiar? Wait, not B is observed, therefore A is highly unlikely. So, if H0 is true, then the data are highly likely to follow an expected pattern. Wait, the data don't follow that expected pattern, therefore H0 is highly unlikely. That sounds pretty benign. That's what you learned at some point. But I'm going to leave the left-hand side the same, and I'm just going to put an example on the right-hand side. Okay? If a person is an American, it's highly unlikely she's a member of Congress. True? Wait, she's a member of Congress. Therefore, it's highly unlikely she's an American. Well, that works. Right? So we ruin modus tollens by putting the probability part on. All right? Inverse probability. This is the problem with stars, right? It's based on conditional probability. The conditional probability that it's based on is the probability of the data given the null hypothesis. How likely is it to observe these data given the null hypothesis is true? What a lot of people think, and I'm sure nobody in this room, that's why you're here, but the unwashed masses at our conferences tend to think it's the probability of H0 given the data, which is just wrong, right? Bayes' law says it's wrong. That's just Bayes' law right there, okay? The problem is, and this is my adjective, it's an unholy blending of Fisher and Neyman and Pearson. And as we heard some story about this morning, I'm going to elaborate on that a bit. What happened was, well, Fisher and Neyman and Pearson hated each other, okay? And if you were a Fisher student, you couldn't talk to Neyman and Pearson. The only person they could talk about, through both camps was gossip. Anyways, and so they fought, they argued. Fisher once likened the Neyman-Pearson hypothesis testing paradigm to the Soviet 5-year plan because it's mechanistic. That's not as mean as you can get in the 1930s, right? In England. What happened was, in the 1940s roughly, textbooks writers, mostly sociologists, they were afraid of offending either camp. And so they sort of incorporated elements of each. Right? So Neyman and Pearson didn't really have a null hypothesis. They had two hypotheses. They used theta A and theta B. Fisher liked the null. It's just something to be nullified. Right? So they blended these two things to get the null hypothesis significance test in an illogical way. And here's why you know it's wrong. Here's something that a lot of the world uses and nobody claimed authorship. Wait a minute. Do you know any academics that don't want to claim authorship of something they created? No, I'll just give it to the world. I don't need credit. That's not, I'll just sit in my office, that's fine. This thing is horrible. Just to point out how bad inverse probability can be, or mistaken inverse probability can be, here's an example that's actually true. Everything else I said is true too. But so in the early 1980s, the Australian government wanted a cheap test to detect AIDS in people. And this is even before we understood the linkage between HIV and AIDS. Okay, so this is really early. So they were pretty sure that the probability of AIDS in the risk group that they cared about was 0.02. Okay? And they designed a cheap chemical test where the probability of correct positive classification was 0.95. What's that called in epi terms? Come on, you know. Starts with an S, and then an E. What? What? Sensitivity, thank you. And the probability of correct negative classification was 0.9. So C is classification, A is AIDS. What's the last one called? Yes, thank you. Okay, so that seems pretty good, right? And it's cheap. Suppose we care about something else. What's P of A given C? That's the probability someone actually has AIDS given that the test classified them as having AIDS. Okay, so they walk out of the clinic with a positive classification. What's the probability, excuse me, that they really have it? We can calculate that. We have everything in that equation except P of C, but we can get P of C from the law of total probability, right? P of C is P of C and A plus P of C and A's complement, right? Well, I have all these things, right? This is just law of conditional probability. I'll do that law of conditional probability, but I don't have that thing, so it's 1 minus that thing, which I have. Thing is a technical term in statistics, right? Right? And so I just plug in all those numbers and I get 0.005 for P of C, plug that in with Bayes' law, and I get 0.38. So wait a minute. Despite those terrific numbers for sensitivity and specificity, the probability that someone really has AIDS after the test says they do is only about 40%. That sounds horrible, right? Actually, that's pretty good from an epi perspective. Why? Okay, what are these people going to do? They just got the cheap test, the cheap chemical test. They're going to go to their physician and get the gold standard test. Right? And 60% of them will be incredibly relieved. You ruined their week, right? You totally ruined their week. But you kept some people from spreading the disease. So it turns out these numbers are almost identical to a home pregnancy test kit that you go buy at the drugstore, right? And it's a trade-off, right? So they want good sensitivity and specificity, so women who are actually pregnant and perhaps will stop drinking and smoking or whatever, right? But some large fraction of those women are going to go to their physician, get the gold standard test, and find out they're not pregnant. So, so I don't know if you're going to ruin their week or depending on what they're trying to do, but so think about this. I just showed you that the interpretation of the hypothesis test gets switched around. This is how different it can be. Yet again, people put stars on tables. Now that I've bashed everything else, I'll get to Bayes. Now that I've told you all this other stuff is horrible, what do we want to do about it? Well, you hold truth things about that today. So a little history. So Bayes lived from, as you see, 1702 to 1761. His famous essay, Doctrine of Chances, was published in 1763 by his friend Richard Price. I like to say Bayes chose to perish rather than publish. And there's been a couple hundred years of conjecture that maybe Bayes wasn't a Bayesian. That the reason he didn't publish his paper was he wasn't sure he was right or didn't believe it. We don't know. That's my picture of Bayes' tomb. It's in Bun Hill Cemetery, about a mile north of the city of London, the financial part of London. You can go see it. It's cool. He's in there updating his priors. And it turns out at the same time, Laplace had basically the same idea. But as you probably know, at the time, the English and the Continentals weren't engaging each other very well academically. And then we get to these giants of early statistics, right? The Pearsons, Fisher, Neyman, Wald, they hated the idea of inverting conditional probabilities and uniform priors. And they were very hostile. And they tried to kill the Bayesian idea. Does anybody, by the way, know why Carl is spelled K-A-R-L?
He changed his name.
Why?
He was very taken by Karl Marx.
Isn't that cool? He was born C-A-R-L and changed. And what journal did he found?
Oh gosh.
Biometrica.
Biometrica.
You should devote your tenureship.
He founded Biometrica. How is Biometrica spelled?
With a K.
Okay.
With a K. Isn't that cool? So that's why he's a big K guy. And then these people kind of kept the flame alive throughout the middle of the 20th century. Jeffreys was a physicist, DeFinetti was a probabilist, Good was, I guess, just a statistician, Jack Good. Jimmy Savage, I love that name, right? He wasn't James, he was Jimmy Savage. I mean, that sounds like a Batman character in the movies, right? Lindley, Zellner was an econometrician. So they kind of kept the flame alive, okay? But what it led to was a world divided. So for a good part of the 20th century, stat departments were either Bayesian or anti-Bayesian. And so, for instance, if you were a PhD student coming out of Duke's stat department, Berkeley wouldn't touch you with a 10-foot pole. Seriously, isn't that bizarre? The sort of classic foaming at the mouth Bayesian departments were Duke, Carnegie Mellon, Harvard on occasion. Anyways, so then what happened, and this is the topic for later this morning, the world changed in 1990 in a really fundamental way. So up until this point, one of the main criticisms of doing Bayesian work, particularly in the social sciences, where we have complicated models about complicated human beings, was that you could specify the model, but you couldn't estimate the parameters. You get this big joint posterior distribution that you couldn't integrate. Either it was incredibly difficult or impossible. Okay? So one phrase was that Bayesians are kind of like unmarried marriage guidance counselors. We can tell you what to do, but we don't do it ourselves. This paper came out in JASA in 1990, and it was nothing but a review paper. And it basically said, hey, there's this stuff in statistical physics and image restoration and engineering that solves this problem, computation. And it just changed the world, fundamentally changed the world. There was a flood of Bayesian articles that came out after that. There's pent-up demand that just flooded out. And now we can estimate virtually anything. Right? We're not limited in any way, and it absolutely changed the world. And now there really isn't this gigantic divide anymore. So, things that changed my life, version 1, microwave ovens, ATM machines, pay at the pumps, and Gibbs sampling. And that's actually a real live Gibbs sampler caught in the wild, which I'll talk about later this morning. So what is Bayesian inference all about? Two primary principles: explicit and direct use of probability for describing things that we don't know. Right? So we're going to use probability models for data, that's likelihood functions, and probability distributions for parameters. So I don't know what the parameters are, but I'm going to give them distributions, right? And then the principle number 2 is I'm going to update those. So using inverse probability, i.e. Bayes' theorem, I'm going to update those distributions, and I'm going to describe them to you. What's the distribution of the unknown theta after I get the data? That's all. Well, I can leave right now, and if you appreciate that, you're way down the Bayesian road. I won't leave. So 3 general steps: specify a probability model for the unknown parameters. It includes prior knowledge, which we all have in the social sciences. Update that by conditioning on the data. And then describe what you have and evaluate the fit of the model and look at sensitivity to certain assumptions like prior distributions. Okay. So in more explicit terms, pi of theta given x, that's the posterior distribution of the unknown theta given the data. That's Bayes' law. It's the prior times the likelihood divided by the integral of that to make it sum or integrate to 1. Okay? So if you were to do that integral, right, you would get p of x. Well, wait a minute, to a Bayesian the data is fixed, so that's a constant. So its main role in Bayesian inference is just to make pi of theta given x integrate or sum to 1. There's one other way we use it, it's called a Bayes factor. I'll talk about it shortly. So what most Bayesians do is they forget about the denominator for a while, and they just say the posterior is proportional to the prior times the likelihood. And you know what? If the result integrates to 1.4, and I don't like that, I'll divide by 1.4 and get a proper PDF for my posterior. Does that make sense? So it's just, it's not important. And why drag that stuff along through a bunch of calculations? So where do we get these priors? Different ways. And strangely enough, sometimes Bayesians argue about this amongst ourselves very quietly in private rooms. we don't want the rest of the world to see this. So empirical Bayes, Carl Morris kind of invented this. Prior distributions produced from other parts of the data. Sometimes the same data. Some Bayesians really don't like that. I like proper Bayes. Okay? That is, priors come from knowledge, things we already know. Okay? Research or intuition, maybe. Hey, if you study something for 20 years, maybe you have some intuition about it. Just a guess. You can also get it from substantive experts who don't care about the statistical process, so on and so forth. Reference Bayes, and this is a surprisingly big group. There are Bayesians who try and create priors, and this can get very, very mathematical, that have the smallest effect on the likelihood function through the calculation you just saw. Sometimes they call themselves objective Bayesians. And again, it's very mathematically intricate at times. They have a conference. And what they do at the conference is they invite one non-objective Bayesian and then totally beat him up during the talk. I've suffered that. Then there's decision theoretic Bayesians, where prior distributions are from one of the last few sources, and then you throw in loss functions and utilities and so on and so forth, and this is a very nice, clean mathematical format. Having said all that, most social scientist Bayesians are what I call Bayesians of convenience. They put flat priors on just about everything, and they really want the engine Gibbs sampling to do heavy-duty calculations. Okay, so those are generally where priors come from. So what happens, Bayesian's preaching that the posterior is proportional to the prior times the likelihood, and the prior is important, the likelihood is important. This is from a recent Bayesian meeting. I think that's Christian Robert. But we practice things like flat priors or normals or gigantic tails or some such things. So we're still moving in a more principled direction. We have a ways to go. So let me give you a very specific data-oriented example of how we do Bayesian inference. So let's just say we have a set of data, x1 through xn, right? With IID from some Bernoulli process. And so we care about p, the probability of a 1, like everybody else. I'm going to put a beta prior on that. Why would I put a beta prior on that? Well, the beta distribution, as you may recall, is bounded by 0 and 1. It's got two parameters, a and b, in my notation. It's very flexible, right? You can make it symmetric and unimodal. You can make it flat. You can make it bimodal and snake up the sides. You can make it skewed left, skewed right, whatever. So that's a great prior to describe p, the probability of a 1. So the first thing I'm going to do is a standard trick. I'm going to just sum up the x's. That'll just help me with notation and whatnot. If I'm after p, it doesn't matter whether I deal with a bunch of binomials, or, Bernoullis, or a single binomial. Okay, so I still care about p. I know what n is. I made the experiment. So let's do the first part of Bayesian inference. So here's the numerator, right? It's the distribution of y given p times the distribution of p, right? The prior. So the first part is just a binomial. We've all seen that a million times. There's the beta PDF over there. Okay? So there's the beta PDF. And I'm going to mathematically sort of collect things. So I've got p to the stuff and 1 minus p to the stuff. Right? Stuff is a technical term, remember. Okay? So that's the joint distribution. What I really need is f of y, right, the denominator, to get a full probability statement. Well, f of y, right, is the integral from 0 to 1 of this thing, right, integrate out p. Then if I can integrate out p from f of y comma p, then I get f of y, right? Does that make sense? But I like doing integrals. I think they're fun. But most of the world doesn't. So I'm going to do this integral without really doing the integral. Okay? So what is this piece here? This is the kernel of a different beta distribution. Right? Beta
distributions are just p to the stuff times 1 minus p to different stuff with some normalizing constants in front, right? So this is a different beta distribution. So what if I kind of came up with some constants in front of this, right? Such that they were the right constants, then this thing would integrate to 1, and I'd be rid of it. Well, the first thing I could do is take all these constants and stick it up front. Well, this is the inverse of the constants I needed to make this thing integrate to 1. You see that trick? So if I had the flip of this right here and got rid of that stuff, this integral would be equal to exactly 1. So this is the inverse of the stuff I needed to stick there. So I'm done, and now I just have a bunch of gamma functions to worry about. Okay. Well, I take all those gamma functions and I shove them in the denominator there, and that looks really nasty and ugly, but you pull out the red pen and you just cancel a bunch of things and clean up some stuff, and you get this. What is this? This is the posterior distribution for p, given the data y. I just use Bayes' law. Well, wait a minute. It's p to some stuff times 1 minus p to some different stuff. So it's another beta distribution, right? It's a different beta distribution than the prior, but it's a beta distribution. That, by the way, is called conjugacy. Conjugacy is when the parametric form of the prior flows down to the posterior. And there's about 8 or 10 special cases like that. And Bayesians in the 20th century, mid-20th century, loved them because the calculations were easy, and you could get them on. So this is a particularly clean and elegant version of it, but the posterior for p is just this beta distribution. Notice that it's a compromise between the data and my prior information. My prior information was how I parameterized the beta distribution, right? So it turns out all Bayesian posteriors, all Bayesian results, are a compromise between prior information and data. That makes total sense. You know what I call that? Science, right? But that's not all, just like the commercial says. That's not all. You get this in too, just for $19.95, plus shipping and handling. I'm going to look for a minute at the mean, the posterior mean of p, the unknown parameter. Okay? It turns out that the mean of any beta distribution is the first parameter over the sum of the parameters. Right? So here's the first parameter in that beta distribution. Here are the sum of the parameters. Okay? And so then I'm going to rewrite it mathematically to get this form over here. Okay? So what is this? That's the binomial mean, right? The data mean. What is that? That's the prior mean. Oh, so wait a minute, this is really cool. The posterior mean is a weighted sum of the prior mean and the data mean. It's a compromise. But wait, that's not all. You get more. 1995, shipping and handling, right? These sum to 1, these two weights, right? That's not always true, but this is a particularly elegant case. What happens when n gets really big to this posterior mean? Well, over here, right, this whole thing goes away. If n goes to infinity, if we're doing asymptotics, or if n just gets really, really big, this is only in the denominator, so it just vanishes, right? Now over here, for any reasonable a and b, right, this thing becomes 1, right? And I just get that. So what does it mean? In the limit, if you have tons and tons and tons of data, the likelihood function always wins. The data always wins. And the prior is unimportant. That makes total scientific sense. If I've got just tons and tons of data, right, I can overwhelm priors, overwhelm a literature review. Right? That makes total sense. Lots of data means priors are less important. Now let me flip it around. Suppose you live in a world where data is really hard to get. It's really expensive, right? You're measuring aliens, right? And it's hard to talk to them. There's actually a political scientist at Emory that talks to aliens, I swear. Courtney Brown, look him up. So you go to Courtney and he's only talked to 10 aliens, right? And you want to understand aliens. Well, then you want a lot of prior information, right? The literature on talking to aliens, as big as it is. Right? So if data size is small, if it's impractical, it's hard to get, you still can have answers, like my case with 15 data points. So the data always win in the limit,
But for modest or small data sizes, the prior can really help you out. So let's do an example of this. So here's some data from this from a cultural anthropologist, Romney, not the Romney you're thinking about. And he studied something called cultural consensus. And it's basically how much a society agrees about important stuff. Okay? So in this particular case, he went down to Guatemala and he interviewed peasant women in the countryside, obviously. And he asked them, is polio contagious? And his idea was, if they can't agree about that, right, then, you know, the other stuff, the easier stuff, is going to be, you know, it's sort of a limit on agreement, right? So, there are the responses. A 1 means they think polio is contagious, and a 0 means they don't think it's contagious, right? And I'm going to put 2 priors on this. The first is a beta 15.2, okay? And what is that? That's my read of what Romney wrote about in multiple articles. That's what I think he thinks. He's not a statistician, but and then a beta 1.1 is a flat prior. Now, we know that a flat prior, a uniform prior, is not a no information prior, but it's a low information prior in some senses. So I'm going to contrast those two. Now, I don't have to do any complicated calculations because I already just did them for you. So here are the posteriors, a beta 32.9 and a beta 18.8. Now you're thinking, oh wow, what a big difference that is. That's kind of hard to visualize, so we'll do it, right? So the first, the upper box, the gray distribution is my prior, my Romney prior, and the gray line down here is the uniform prior, and the dark lines are the posteriors that result. Now, a couple observations. One, you see that they're not radically different, right? So the data had a lot to say here. Even with the modest size that it was, I think it was 20, right? The data had a lot to say. However, with the uniform prior, this is a little move towards the middle, right? The Bayesian highest posterior density interval is a little wider, right? And so we can make these contrasts. By the way, the interpretation of this is what your undergraduates wanted the confidence interval to be. That is, there's a 0.95 probability the effect is in here. I can do that because I'm a Bayesian. And I described everything probabilistically. You're allowed to ask questions. Okay, let's do a more sort of realistic social science model. I didn't pick this example because we're in Texas. So it turns out every year about half of the executions done in the United States are in Texas. Do you know that they don't even do it at midnight here anymore? Like most states do it at midnight. And I looked into why that is, and I thought there's some legal reason for that, right? So one person's shaking their head. Why do states do it at midnight?
Power piece, wasn't it?
Power?
Was it related to electricity?
No. That's a good guess, though.
It's superstitious.
Say that again?
It's superstitious, isn't it?
It turns out it's to cut down on protests. Isn't that funny? Although those are terrific alternative reasons. And so about a decade or so ago, the state of Texas decided they didn't want to do that anymore because they don't have protests generally, and they don't want to pay overtime. So then now they do it during business hours, 9 to 5. Anyways, so suppose we wanted to model applications of the death penalty by the 50 states. You know, and maybe we care about ideological, racial variables, religious variables, political culture, things like that that were measured. Now, however, 15 states at the time did not have a death penalty on the books, right? So, like, you can have all the cultural inclinations you want, but the law in Hawaii says you can't execute convicted murderers, okay? So we've got to have a fancier model, okay? So the deal is, right, if there was an underlying metric and we had all the data, we'd have just some straight linear model. Z is equal to x beta plus an error term, and we'll put a normal assumption on that. But what we have to do is we're going to say, if we see the data, yi is zi for zi greater than 0. And if yi is 0, if z is less than 0, so we need a model for that. So it turns out we just modified the likelihood function a little bit so it has this extra piece here to account for the z's that are less than 0. So it's a latent model on the z dimension. Okay, so we're incorporating those states without a death penalty. Well, I'm a Bayesian, so I'm going to put priors on these things. So the conjugate priors are normal for the betas, for the regression coefficients, and the inverse gamma for sigma squared. Those are conjugates, so they flow nicely. The calculations are relatively easy, except this calculation, this likelihood function is a little bit awkward, so the priors on there is a little awkward. So I actually need to use the Gibbs sampler, right? Because this is my posterior. Now, here's what we could do. And this is why Gibbs sampling Metropolis Hastings is so important, is until 1990, if I just gave you this model, and this is not a ridiculously complicated social science model at all, it's one of the standard things in our toolkit. I would have to pull out the yellow pad and the mechanical pencil and integrate out each of those betas one at a time, okay, and the sigma squared. That is either highly unpleasant or impossible. So Gibbs sampling solves that problem for me. We're going to do this later in the morning. Basically, I'm going to set up a Markov chain that runs around the surface, how many dimensional surface, like the 10-dimensional surface, whatever, and explore it for me and summarize it. So the computer does the hard work for me. And at the end of the day, right, I get results. So what the Gibbs sampler does is it takes these conditional distributions and it cycles through them from a starting point. That's a Markov chain. And it cycles through them and then produces eventually marginal values. I'm going to talk about it later in the morning. It's magic. It's really cool. And then here's a Gibbs sampler running around. And then I get a regression table from that. And so I'm describing this in relatively un-Bayesian terms in the sense that Bayesians like to think about distributions, but there's no reason I can't take a posterior mean and standard error. Right? And if it goes to a journal that's not known for being highly Bayesian, this is a table anyone can understand. Right? So it turns out pass rates of executions are really good predictors of future executions. Big surprise. Send it off to science or nature, right? Okay. I want to do a really important example, and then we'll take a break. So, did Vinnie Johnson have a hot hand? That's something everybody worries about. So Vinnie Johnson played for the Pistons in the 80s, and he was their sixth man, the guy that came off the bench at 4 times. Okay, his overall shooting rate for his 380 games of his career was a very respectable .43. Right, that's pretty darn good in basketball. So Xi hat, I'm going to label .43. So I tell my students, when you make slides for a conference or something, always have lots of Xis and Zetas, because they're intimidating and cool looking, right? No, don't use thetas. Everybody knows about thetas. So the question I want to ask is, did he have extra game-to-game variability over the binomial? So his reputation was he was a very streaky player. Does anybody remember Vinny? Oh, God, terrible. Well, now you know all about it. So he was the sports journalist called him a streaky player. That is, he would go in and he'd be really hot one game, 9 out of 10 or something. And then the next game or a couple games later, like 1 out of 15 or something. Like he was either really hot or really cold, streaky, right? So I want to test that with data. So I can have a null distribution. It's not a null in the way that we discussed earlier this morning, but I want to have an alternative distribution to feed off of. So my alternative distribution is simply going to be that yi, his shots, are going to be binomial n sub I with some underlying fixed p. Okay? It's n sub I because I can't go back retroactively and confine them to 10 shots a game or 20 shots a game. Right? So I have to index n by I. But the key piece in this null, I really shouldn't even call it a null, it's the non-streaky hypothesis, is that p is fixed. So if he was not streaky, if he was consistent, he'd have a fixed p. So one of his contemporaries, Larry Bird, I hope you've heard of Larry Bird, thank you, one of his contemporaries, Larry Bird, absolutely had a fixed P. Larry started the game, Larry played most of the game, game to game to game to game, he was so consistent, right? That's why he's in the Hall of Fame, or one of the reasons he's in the Hall of Fame. He was consistently good, I should say, is why he's in the Hall of Fame. So that's one hypothesis. Here's another hypothesis, that P is indexed by I. That is, here's what Vinny did, is he's a 6 man, so he tears his sweats off, and there's a bucket next to where he is, and he reaches into the bucket, and it's full of P's. And he pulls out a P, and he says, oh, cool, I'm going to shoot 0.6 today. Puts it back in and goes into the game and shoots 0.6, right? So P is now indexed by the game, right? And so if that P has a lot of variability, then he's streaky by at least one definition, right? Does that make sense? Okay, so I'm going to say P is indexed by I, and then I got to give it a prior, right? Because it's an unknown quantity, and I'm a Bayesian, and everything I don't know, I put a distribution on. That's what I do. So I'm going to make it a beta distribution like you saw before. So there's a theme running through this. And it's going to be beta xi over omega, 1 minus xi over omega. Remember, the beta distribution has 2 parameters, so I'm just parameterizing it in a like weird and scary way. No, it turns out that's going to be handy. Okay? So remember that the beta mean is the first parameter over the sum of the parameters, so it's this. But when you clean that up, you just get xi back. So you see the logic of doing it that way, right? Okay, so I have 2 hypotheses. I have a prior, right? So it turns out the variance of the beta, and this is something people rarely memorize, is this, right? And I'm gonna, it's a little more complicated, but I'm going to clean it up so I just have that. And the reason I have this omega parameter is I knew it was going to be in that fraction in the denominator. So as that thing goes to 0, what happens, as omega goes to 0, what happens to 1 over omega? Come on. Who said that? Yes. It blows up, to use the technical term, and smoke comes out of the back of your computer, right? So that thing, if that blows up in the denominator, right, then the variance of p sub I goes to 0, right? And that means he's not a streaky player. Well, I didn't say it in the last slide, but his nickname was the microwave. Any idea why? This is sports writers talking. So, you know, the bar's coming. Because he heats up in a hurry. So he was nicknamed the microwave. So as that omega parameter goes to 0, h1 goes to h naught, right? It becomes unstreaky. So what it means is that I can stick in any omega I want, and I can get a range of hypothesis tests that I like, right? So I can test a hypothesis that the effect size is small, or the effect size is large, depending on that omega. And so what can I do? I can actually do 100 hypothesis tests by having 100 omegas, right? And they're all principal Bayesian hypothesis tests. I'm being overt about all my assumptions. So the way I'm going to do that is with a thing called the Bayes factor. And the Bayes factor is the probability of model 1, given the data, over the prior for model 1, divided by the posterior probability for model 0, given the data, divided by its prior. Now, wait a minute. I told you, Bayesians, everything we don't know, we put a distribution on. We make a probabilistic statement about it, including what's the right model. I don't know for a fact what the right model is, so I'm going to put a prior on it, okay? So it's the ratio of the posteriors for the models divided by their priors. Well, what most people do is they make the prior on model 1 0.5 and the prior on model 0 0.5, so you don't worry about that part. You can change that if you like. I'm not going to do that. And so what I have in this little table here is different values of that omega parameter, which give me different variances of p, which give me different Bayes factors. And the deal about the Bayes factor is, if it's much bigger than 1, you have evidence for the model in the numerator. And if it's much smaller than 1, you have evidence for the model in the denominator. And there's no cutoff points. There's no alpha involved. Okay? There's nothing like that. You don't need that. Now, it's a little annoying when you get 1.1 or 0.9.
But when you get 10 or 0.1, you're happy, right? And there are some, some people have proposed cutoff points, but we all know that they're rough, and we were not going to be slavish about them. But in this case, it's pretty clear. So when omega is 0.001, I've got a very small variance for Vinny. And the base factor is 0.21, which pushes me towards, obviously pushes me towards the non-streaky model, the null. I really don't like saying null, the fixed P model. Oh, well, I don't like that. So what if I start making omega bigger? When I make omega bigger, I'm adding streakiness. In the last graph, I'm moving the alternative hypothesis out this way to make the effect size bigger. Oh, but wait, it does make the variance bigger, not a whole lot, unfortunately, but the base factor is diving. So what this says is there is no evidence that Vinny really was a streaky player. So what's the real story? What's the substantive story? Sports writers have to fill pages. So they make stuff up. They take a sample and they make it a principle, right? And then they get to write about it and argue with each other, and that's how they put stuff in newspapers and magazines or on the air. So I think this is a good point for a break, if I don't have any questions or concerns.
I have one question.
Thank you.
Oh.
I was hoping for that.
What
It's
is
about basketball, right?
Well, I can ask about cricket. What is the difference between a non-informative prior and a less informative prior? For example, if I have a uniform prior on correlation, right? Correlation can go between -1 and 1.
Yeah.
So I just naively say uniform between -1 and 1. What would you call that prior as?
I would call that a low information prior. So there was 100 years of arguing about uniform priors. And the basis of the argument was, is a uniform prior a no information prior? And the answer is a resounding no. Okay? So some of the early Bayesians thought it was a no, Bayes thought it was a no information prior, or posed it as a no information prior. We know it's not a no information prior. If I tell you how many, there's like 16 Republican candidates right now in the primary. If I told you they're all equally likely to win the nomination, that's information, right? That's strong information. So we know that the normal is not, but it's often used as a benchmark for a low information prior, because we all kind of understand what its implications are. What the objective Bayesian crowd tries to do is come up with an even less influential prior. And that is, for this exact likelihood, and not any others, which prior moves the likelihood the least? So the likelihood looks almost exactly like the posterior. And they think principled reasons for doing that. I don't think that's very Bayesian. The math is really cool. Jim Berger is kind of the grandfather of that approach. He's a dude. So these uniforms are kind of just used as a, well, how far am I from that, right? I don't think that's very important. I like proper Bayes, where I say, hey, look, I know stuff. If you don't believe I know stuff, don't read this article, right? And I'm kind of circuitously answering your question, I think. Sometimes they're kind of handy as that reference, and I'll give you an example. So years ago, my PhD student, who by the way starts here next year in political science as a senior professor, he was interested in the judicial system in Nicaragua after the Sandinista government fell, and what people thought about it. And so he had some grant money, he went down to, not Nicaragua, I hope I said that. He went down to Nicaragua, and he wanted to interview people in the countryside about what they thought about the fairness of the judicial system after the Sandinista government. And it turns out he couldn't get a very good sample. Like, he would walk up to them and want to interview them about the courts. And, this is after the Sandinista government fell, and, it's like, what is this person doing? And even though he speaks perfect Spanish, he's African-American, and they thought he was Cuban because of the Spanish and his complexion. And so, like, what's this Cuban doing asking me about the courts? And am I in trouble with the courts? And, so he had a really hard time getting a good sample. And so we came back, we got some additional grant money, and what we decided to do was to interview elites to build priors. So elites on the left, elites on the right, and then judges. And we got about 3 or 4 of each group. And it turns out they were very willing and positive about talking about the courts and how the courts worked after the Sandinista government. And so we had a modest sample size of about 90 or 100 from the peasants, and then we had these 3 flavors of priors, okay? And what we did is we did 3 models, and the way the paper got written was, this is how the peasants, the rural peasants, think about the court through the lens of this elite, or this elite, or that elite. And it turned out the priors were interestingly different, okay? Goes off to the journal, and we had a bear of a time with the people that just studied Central America, not the model people. But one of the reviewers insisted that we have a 4th column down the regression table that had a uniform prior. And I was really against it, because that's not what we're doing. We're using real information to shape a posterior based upon a perspective. And what does the uniform mean in that context? It means nothing. But I'm well aware of the following fact. People that are dogmatic with reviewers have fewer publications. Right? For all you grad students out there, remember that. Right? The people I know that are absolutely dogmatic, this is my paper, this is my research, have fewer publications. So we put that 4th column of uniforms down, and I think we had 1 sentence that referred to it. Oh yeah, by the way, if you want to look at a reference over here, that's a uniform column. And I wanted to put it in a footnote. So it's contextual, right? In that case, I think uniform is meaningless. In the Romney case that I did, I think it was interesting, right? Because it's so flat, it's all over the posterior space, and yet it didn't radically move that posterior, which meant that the data, even a modest-sized data set, had a lot to say in that context. So is that kind of what you're after?
Yeah.
Okay. Long-windedly. Anything else I can go on about for 10 minutes? Maybe you want to break, right? So what's the structure for breaks? Anybody in authority here?
Oh, just take a 15-minute break and come back, and we'll resume at about 10:30.
It's a 19-minute break. Great.
Okay. Oh, okay. A little before 10:25 then.
Oh, I should have said that.
Remember, she